Hobby-Eberly telescope dark energy experiment, or HETDEX, and the tremendous amount of data that Virus has provided for HETDEX. Well, everyone, we're in for a real treat tonight because it's a great honor and pleasure for me to introduce our speaker tonight, the man who has been the main driver behind this program since its conception at least over 20 years ago, Dr. Karl Gebhardt. So Karl grew up in Rochester, New York. His career has taken him through Michigan State University, Rutgers University, University of Michigan, University of California at Santa Cruz, and eventually to the University of Texas in 2000. And how lucky you were that you made that, that trip to Texas. He's now the Herman and Joan Suit Professor of Astrophysics there, and he's also the chair of the Department of Astronomy at UT. He works on a variety of galaxy studies, ranging from black holes to dark matter to dark energy. He's won numerous awards, including the Northeastern Graduate School Dissertation Award in 1995, a Hubble Fellowship from NASA in 1997, a Teaching Excellence Award from both the University of Texas in 2003 and the McDonald Observatory Board of Visitors in 2004, and a National Science Foundation Career Award in 2004. And in 2012, he received the Edith and Peter O'Donnell Award in Science from the Academy of Medicine, Engineering, and Science of Texas. So Karl works with numerous undergraduate and graduate students and involves them in all levels of his research, which I think is really great. Much of his career is focused on understanding the role of black holes play in the formation of galaxies. His current work is focused on the understanding of dark energy with the HETDEX program, which he currently leads. The unique approach to studying dark energy is designed to measure any evolution that there is in the expansion of the universe and to illuminate one of the great scientific mysteries of our time. Well, the HETDEX service is now complete, and it contains an unimaginable 1 billion spectra and over 1 trillion resolution elements. It's an absolutely incredible wealth of data that will enable a variety of scientific studies that Karl is going to highlight for us tonight. So let's give Karl Gebhardt a big TSP welcome.
Thank you all. It is a pleasure to be here. I come out here often. So I'm based in Austin. I come out here about once a month, once every other month, and I take data or meetings. And normally when I take data, I'm alone at the telescope, which is pretty cool. It's pretty cool being alone in the 2.7 meter dome. That is just a very special experience. Coming out here now, what I did is I walked around earlier and I saw all the telescopes before everyone was up there, and it just kind of blows me away. I catch my breath when I see that, because all of you, you really appreciate the serenity, the depth that you get just by being in the middle of nowhere and looking at the dark sky. That doesn't really, you don't really get that as a professional astronomer. Normally, you get data from the space telescopes. You don't go to the telescopes much anymore. And you're going to hear about a program that I'm working on to get people to the telescope. It really makes a difference. And it really excites me when I'm around groups such that as you who just love the skies. So what I want to do is talk to you about HETDEX primarily, but I cannot not talk about black holes. Black holes are what I started out with. There's a lot of flies here. What I started out with in the when I was first doing astronomy, and that really set me on my path to trying to understand what we can't see based on objects that we can see, because you can't see a black hole. I started out in globular clusters. I don't have to explain to you what globular clusters are, which is awesome. And so that was my PhD thesis, and M15, I'm sure you've looked at M15 at some point. I probably spent 3 years of my life on M15 And when I think about that is absolutely crazy. That was all I would do. Back then you're working 70, 80-hour weeks. My graduate student, Mahan, is in the back right there. Raise your hand, Mahan. So I'm going to tell him my 70, 80-hour week, Mahan, is what we do back then. He works that much. And that's all I did, work on a globular cluster. And I had a case that had a black hole. I went back and forth for a while. And then I started to apply that to galaxies. And so you have a couple galaxies here. There's the biggest globular cluster in Andromeda, M31G1. That's the one that has one of the most obvious black holes out there for globular clusters. And then you have the biggest galaxy in the nearby, one of the biggest, NGC 6166. All these have black holes. What we found, the big thing that actually got me my job as a faculty member was I led a team that showed that every galaxy had a black hole in its center. And it told us something fundamental about how the galaxy forms. And I'm going to come back to this because we're getting observations on James Webb Space Telescope that is just blowing us away. And I actually sometimes get goosebumps when I think about what we're learning over the past 1 or 2 years. On the bottom is a dwarf galaxy called Leo 1. This is the one that we did a black hole mass measure in that some time ago, and it led me to a project which I'm going to talk about towards the end of the talk tonight, where I'm bringing undergrads out to the telescope to observe these things. So let me talk a little bit about black holes. This is M87. This one I spent 3 years as well. You probably have seen images of M87 and observed it in your telescopes. So there's the big ground-based telescope over on the left. And then on the right are the zoom in from the Hubble Space Telescope. This one I was very happy with. This object I spent 2 weeks of time on the 2.7 meter, I don't know where it is, up there, and just taking data on this object here. I came up with a very massive black hole in this galaxy. It was about 3 to 4 times more massive than what anybody else had. I did that because I had crazy amount of data that I can get on these telescopes. We own the telescopes, so I can get a huge amount of time. And I had a very sophisticated model that I used. And I measured this black hole about 3 to 4 times bigger than what anybody had ever seen, and everyone thought I was nuts. They said, that can't be right, no way. And what happened is then later on, there was this image here that I hope you've all seen. I consider this image the most significant image in the history of astronomy. And let me explain why. So I compared this image to the sketches of the moons of Jupiter that Galileo did. I compare it to the pale blue dot that Carl Sagan asked NASA to turn the satellite around and take the image of the Earth as Voyager was going out. This image is the black hole in the middle of the M87. And you probably have seen it, I'm sure you're aware of it. Every time I look at it, this thing blows me away. What you're looking at in the middle is the black hole. You have gas behind it. The light from the gas is emanating out, and the black hole, because it's distorting the light, causes that gas to go around. You get this donut. But what you get here, in that middle part, you can measure the diameter incredibly accurate. And once you get that diameter, you get what's called the Schwarzschild radius. That's the radius of the black hole. You just get the mass of the black hole, just from that alone. So I did my black hole mass for this galaxy back in 2010. This image came out in 2017, 2018, and everyone told me on the team, I can't tell you what the black hole mass is, but you're going to be happy. They came up with a black hole mass that was within 1% of the mass that I got. And I got a lot of congratulations that day. It was a lot of fun. But it goes to show that if you work incredibly hard, get really good data, trust your models, put it out there. It may be controversial, but you know what you're doing. And so that's a lesson that I try to get to all of my students, is just trust what you do. But this image is showing that these objects are black holes, and what we're beginning to understand now because of this is the concept of space-time. I'm gonna hit you in the head with space-time over and over and over again. Space-time, it's not just a Hollywood Star Trek-y thing, it's a real entity. You cannot say anything about how gravity works or how, an objects move around in the universe without understanding, without having a concept for what space-time is. And we are nowhere near on Earth be able to probe the physics of space-time. But by using a system such as this, where the density is so incredibly high, we're beginning to get a handle on it. And so here we're beginning to understand the physics around the black hole, and we can model as the material moves around. So this image has been incredibly powerful for that. There's another instrument that's out there. So the black hole image was taken by the Event Horizon Telescope. The other one that's out there is LIGO, the Laser Interferometer Gravitational Wave Observatory. This is where they're actually measuring the merging of two black holes. And when they merge, they vibrate space-time because they rotate, they vibrate space-time, that space-time oscillates, it comes to Earth, and it expands and contracts space. And we can measure that expansion and contraction. And so now we have hundreds of objects that we know are black holes, where we can measure their mass incredibly accurate. We've never been able to measure masses this accurate, and we know roughly where they are. We can't pinpoint exactly, but we're finding these black holes. What is amazing is that all of the black holes that were discovered before LIGO were about 1 to 10 times the mass of the sun. Or black holes that are about 1 million to 1 billion times the mass of the sun. When LIGO was first turned on, the black holes it found were all the ones in between tens and 100 times the mass of the sun. And this is the one that really, oh, okay, yeah, I do need water, don't I? So now we're finding these black holes in detail, and these are the ones that I'm going to argue are in the middle of globular clusters. So I'm going to try to bring everything together, the concept of space-time, the concept of what a black hole is doing to a galaxy, and then related it to a globular cluster. Okay, so that was another huge advance. And then, this is the one that I talked to you about that gives me goosebumps, is that James Webb Space Telescope now is finding these galaxies in the very early universe. That work is being led by the University of Texas, by faculty members in the Department of Astronomy. And we're finding incredible numbers of galaxies, way more than we thought. Not just that, we're finding that these things have black holes. And they have very massive black holes. And in fact, it looks like the first objects to form now that we're discovering are black holes. And not just that, these objects are almost all black holes. That is, when we look at a galaxy nearby, we find a black hole that is about 0.1% of the galaxy's mass. The black holes that James Webb Space Telescope is finding are dominant. They're over 50% of the mass of the system. And here's a construction of what the model will look like. It's a black hole in the middle with a lot of dust around. And we have a colleague, John Chisholm, who came up with a new model that I have been calling revolutionary. His paper was just published was just accepted yesterday. It'll come out in a couple of weeks. We'll do a press release. It's a model for what these early galaxies are. These things, we call them little red dots. They're small and they're very red. We call them, there's a lot of these little red dots. His argument that these things are globular clusters in formation. They're supermassive stars in the early universe. They're in the center of a globular cluster, and so they're a globular cluster in formation that leaves a black hole. Why I am so excited about this is that globular clusters were the first objects that we basically used to tell us the structure of the galaxy and the structure of the universe. This is the stuff that were observed in the 1800s. You've observed many of the Messier objects. Messier was back in the 1800s. And so what is going on is we're now having a new model for how these globular clusters actually form. I started my thesis, my PhD was on globular cluster back in the mid-90s, and I would never have predicted this. No one had a model like this. John Chisholm came up with this beautiful model. So pay attention, this is just coming out, and it's explaining where globular clusters come from, explaining where the first black holes come from, and explaining these weird objects that James Webb Space Telescope is finding. And so I just wanted to get that out because it is really exciting right now. Okay, well, what I really want to talk about is HETDEX. HETDEX is my baby. This is the Hobby-Eberly Telescope Dark Energy Experiment. I came up with the idea for HETDEX in 2002. That is 24 years ago. I came up with the idea. It was a hallway conversation. At that time, we knew that a dark energy was out there. And so I wanted to use our giant telescope, the Hobby-Eberly telescope, and to make a giant map of the universe, and then try to understand what dark energy is. And I'll walk you through that, and we're done. And we have results. I'm trying to get the results out, but I have a number that I'll show you. This was a large collaboration, but what was nice about it is that we own the telescope. The University of Texas owns 70% of the telescope. So we were able to do a large project. There's a few things we did here. We did this. We used one of the biggest telescopes in the world. We put on the largest number of spectrographs ever considered. We have 35,000 optical fibers. Every time we take an image on that telescope, we get 35,000 spectra, which is crazy. All the data is being stored and analyzed at the Texas Advanced Compute Center. That's one of the most it is the most powerful compute system that is available to the public. And we're doing the largest survey in terms of time on a big telescope. These four things really make this project huge. We had a few collaborators. We have Penn State. We have the NSF, TAC. There's a couple in Germany and in England, but it was really designed, led, funded 99% at the University of Texas. And so, and it's done. So, I mean, I think about working on the same project for 24 years. That, I used to get depressed when I would think about that I studied the same galaxy for 3 years. This is the same project for 24 years. Did you? Okay. Okay, so let me explain what HETDEX is doing and why we designed it. So we know of 3 things in the universe that have important consequence for the expansion of the universe. There is normal matter, what we are. What is so in that in the yellow normal matter, that is the periodic table. Okay, everything in the periodic table is in that little yellow wedge right there, which is a very small amount, about 4%. So 4% of what is in the universe is in the periodic table, normal matter. We On Earth, we're completely irrelevant. We're down to the Earth, and Earth-like systems are about 0.03%. So the universe is completely oblivious to us. Then there's dark matter. Dark matter is about 21%. I'm not going to talk about dark matter. Dark matter is what we think is a new type of particle that surrounds galaxies. It causes stars to move faster than what you would think. Dark matter, so I would say about 15 years ago, whenever I would give a talk, I would say we are about 1 year away from finding the dark matter particle. 10 years ago, I switched to 2, and a few years ago, I switched to I am not convinced that dark matter is a particle anymore. That it could be, again, a misunderstanding of our force laws. Doesn't appear to be, but we are finding no direct evidence of the dark matter particle. Extremely frustrating. Huge amounts of groups and money, and nothing yet. And then there's dark energy, which is about 74% of the universe, and that is just a big nothing. And so I will talk about what dark energy is, but this, think about it. 95% of the universe is in stuff that we know nothing about. That is remarkable. I mean, I can't believe we get money, when we don't know 95% of what's going on in the universe. But we're going to figure it out. Okay, so here's a cartoon of what the universe is doing, and I'll tell you where dark energy comes from. So our universe we live in a four-dimensional world. You all appreciate a four-dimensional world. You have 3 dimensions of space and 1 dimension of time. You knew to come here at a certain time to meet up. That was time, and you had the 3 coordinates. And so we live in a 4-dimensional universe. And now I got to show that on a 2-dimensional structure, so you have to bear with me. So in the bottom left is the Big Bang. All matter is compressed down to a very small spot. All matter in the observable universe is compressed down to a very small spot. And then something happens. Talk about that something later on, but something happened in the universe that causes it to inflate. We call it inflation. We don't have a good idea for what's going on there. And so the universe expands very rapidly. And so I'm trying to show the expansion there as the size of the horn, the diameter of the horn there. Again, bear with me that we live in a 4-dimensional world, and this is a 2-dimensional plot. Time axis is running up along the diagonal. So inflation happens, and then the universe begins to, it expands really rapidly early on, but because of the mutual gravitational attraction of what's in the universe of the galaxies, that expansion should slow down over time. Because gravity is going to cause things to slow down, to come together. When we went out and measured that, and there was one spot here where we measured it, it turned out that the universe, and you've heard the story, that the universe is it's not decelerating, it's not slowing down its expansion, it's actually increasing its expansion. It's accelerated. That's what got a Nobel Prize about 10 years ago. And then it expands out, and that's that. It just keeps on expanding out, keeps on accelerating. We do not understand what is going on. This is why this is considered one of the biggest mysteries in science, because it's something incredibly fundamental that we are missing. The amount of energy, that's where in that previous pie chart, the pie chart's up there, at 73%, 74%, that number comes from trying to explain how much is expanding. So the expansion requires 73, 74% dark energy. That's where that number comes from. Okay, so how do we do this? So we use the Hobby-Eberly telescope. I hope you've all had a chance to see it. You'll see cables on the side of the telescope. That's the 35,000 optical fibers. I was on a review panel for a $500 million Department of Energy facility called a DESI, and they have 6,000 optical fibers. And I was sitting next to the head of the Department of Energy, and she turns to me and she goes, "Man, they have 6,000 fibers. That is insane." I didn't tell her that we have 35,000. I just let it go, and I reviewed the project, and it's all good. She probably knows, yeah, right, you don't tell the head of the Department of Energy that we're bigger than you. So this is the story, and this is what you probably all appreciate when you go and look at data. What we're doing is we're making a giant map. And so what happens, there's a galaxy up on top, at the edge of the universe. A galaxy 13 billion light years away. Something happens in that galaxy. Two clouds of gas come together. Or there's a hot jet coming off of a black hole. It excites a cloud. It excites a hydrogen atom. The hydrogen atom has an electron, goes up in energy level, and then it falls because it got excited, and then when that electron falls back down, it emits a photon. 13 billion years ago. Then that photon travels through the universe. As it travels through the universe, things are happening. The universe is expanding, so the wavelength of that photon is being stretched. There's material that it's going through, so it gets bent because of the distortion of space-time. There's information in that photon of the path it took through the universe. That photon travels towards the Milky Way galaxy, towards the solar system, towards the Earth, towards West Texas. It's been traveling for 13 billion years, and then it takes about 10 to 20 nanoseconds, and it bounces around in the HET, goes into our telescope, and then we get it into our detector, and we turn it into an electron. That photon gives up its existence, turns into an electron. Same thing happens when you're looking at an object through your telescopes. That photon traveled for however long, not quite 13 billion, you can't quite see that far, but there are 13 billion year photons going through your telescope, for sure. And they bounce around in your optics, and they go into your eye, cause a chemical reaction, sends an electrical signal to your brain, and you see it. That photon, so appreciate that photon, because it's traveled a long way just for you to see where it comes from. So that's why we work really hard. And it turns out, for us to detect a single galaxy requires about 280 photons. I know this number because I've calibrated it well. And so you want the biggest telescope possible so you get all the photons coming from that object in that exposure time. And then we can detect it. Okay, this is the plot of $40 million, 24 years, an incredible amount of time from people. This is the bottom line plot. This is it. This is what, and so I want to explain this. And this is telling us, and I'll come back to this and I'll explain it more, but this plot is telling us how fast the universe was expanding 12 billion years ago. There is a peak over here on the data, and I'll come back to this because I do want to walk you through it. And what we're using is that peak is telling us how much the universe expanded. So what we're doing in the HETDEX data is we're taking all of our data, our 1 billion spectra, our 1 trillion resolution elements. We're measuring 1 million galaxies. We're making a map, and we're using that map to see the peak of where all the galaxies are, and there's the peak there. I measure the exact location of that peak. And then this is the bottom line plot. This is the end. I have told my board, my colleagues, that HETDEX is basically a one-number experiment. We're going to take an insane amount of data, and the goal is to measure one number, and that's the expansion rate of the universe as it was 12 billion years ago. And the error bar, but that's a number. So here's the idea. 2000s, we came up with the idea, myself, Gary Hill, Phil McQueen. Mid-2000s, we designed the survey and we started to raise funds. We got an equal amount from the NSF, philanthropic, and in-state, the state of Texas contributions. 2018 to 2016, we built the instrument. The instrument was a little more, we thought it would take us 3-4 years to build it. It took us about 8 years. No one has built an instrument like this before. 2017 to 2024, that's when we did the survey. I'll show you that in a moment. 2025, the reductions are done, and the analysis is basically complete at this point. And so I'll come back to this plot. I just wanted to pop it up there because this is, you know, it's not like a beautiful image, but this is beautiful. It really is beautiful. Okay, so history of dark energy, and then I'll come back to what HETDEX is. So you probably are familiar with this. 1919, Einstein comes up with a concept of dark energy. 10 years later, Hubble shows that the universe is expanding, and Einstein used the fact that it wasn't expanding to come up with the concept of dark energy. As soon as he found out it was expanding, he calls it the greatest blunder of his life. Then dark energy went into the dustbin of history, and then in 1998, 2 teams went out to try to measure the deceleration of the universe, and it turns out it was accelerating, and so the dark energy reared back up. Now let's get back to dark energy. There's an equation down here that some of you have a T-shirt on with that. You can buy this equation at the gift shop at McDonald Observatory. I was given a public talk. There was a chalkboard. I wrote the equation out on the chalkboard, and Sandy Preston, who was heading outreach at the time, thought, "Oh, this would be cool." She took a picture of it and put it on a T-shirt. So that's actually my handwriting on that shirt. So here's the equation. There it goes. And it's a relatively, as far as equations go and what we're doing in physics and cosmology, it's relatively simple. And I want to make one very important point here. On the left side of the equation is observations, expansion rate. Expansion rate is a relatively easy concept. You measure how far away an object is, and you measure how fast it's moving. You do that for as many objects as possible in the universe, and that's the expansion of the universe. You can see, here it's moving that fast, moving that fast, moving that fast. That's relatively straightforward. On the right side is the theory of what's in the universe. There's radiation, photons. We know today the universe has expanded so much that the photons don't have a big impact. Very early on they did. There's matter in the universe, both dark matter and normal matter. And then there's the shape of the universe where it's open, flat, or curved. That, again, doesn't have a big impact. In 1998, we only had the first 3 terms. And what happened is they did the observation, and the left side of the equation turned out to be 3 times higher than the right side of the equation. And there was a collective, what are we going to do? And like any good scientist, you add in a term. And you call it something that sounds important. You call it dark energy. And what I've always said, I think it's on the back of the shirt, the quote says, "It may not be dark, it may not be energy." That dark energy is our ignorance of how the universe is expanding. And it can be seen very well in this equation here. It's the term that we had to add in to make the math equal. And we don't know what it is. So that's where we are. So a few ideas. There's the cosmological constant. Let me explain that, because that's kind of the easiest idea that most people subscribe to. We are humans in this room. We have mass. We could calculate the gravitational attraction to each other. You can actually do that calculation. I know your mass. I know the distance. I can do the calculation. You can do it all relative to me. As I walk away from you, what's happening to the gravitational force between us? It's decreasing because it goes as 1 over the radius squared of 1 over the distance squared. I walk towards you, the amount of gravity, the effect we feel of gravity is increasing. Now, there's also the concept of space-time. This is why I want to bring in space-time, why it's so important what we study around black holes. Space-time is a real entity. There's space-time between you and I as well. As I walk away from you, I'm actually increasing the amount of space-time between us. There's more space. Walk towards you, there's not as much space. If space-time has an energy associated to it, okay? As I walk away from you, the energy of space-time is increasing. The effect of gravity is decreasing. At some point, the space-time contribution is going to take over. And it's going to cause the universe to accelerate. That is the cosmological constant. The universe is expanding, and then space-time that gets expanded so far, you have so much space that the energy of space-time dominates over the gravitational pull of all the stuff in the universe. And then, you're toast at that point. The universe expands, and then it expands even more, and you get more and more space-time. The concept of conservation of energy was completely shot out the window at that point. But that is one of the best ideas out there. There is modification of general relativity. That is changing gravity. We still don't understand how gravity works. We've modified gravity a few times in the history of science. Einstein knew he didn't have the answer right. Newton knew he didn't have the answer right. And so maybe we just need to modify it again. Maybe that equation that I showed you before, it may not be dark, it may not be energy, it could just be a misunderstanding of what gravity is. That's not that hard conceptually to believe. Then the fifth force, a quintessence is what it's called. The fifth essence is a new force. That means a new particle that's out in the universe. We invented dark matter particle, and no one seems to care, and everyone seems to think that there's a dark matter particle. You probably think there's a dark matter particle, right? That's probably if you know anything about dark matter, you probably think like dark matter is probably these flies that are flying around here. The dark matter is thought to be a particle. Why not have a dark energy particle as well? And so people have thinking about that. Those are the ones on the left, and then the ones on the right are just the crazy ones. So the crazies on the right, and then the ones on the left are the mainstream ones. There is one that I like on the right called the Hubble bubble, which is my favorite one, which is one of the ways I built the HETDEX experiment. That is, one idea of our universe is that our universe, our observable universe, is in a tiny underdensity, just a slight underdensity, basically a bubble. And so there's a galaxy, like a sheet of galaxies, a shell of galaxies just on the outside that we can't see. But if there's a galaxy in our view, it will feel the gravitational pull going out, and it will look like it's accelerating away from us. And we can't see what it's pulling into because it's beyond the observable universe. I'll come back to that in a moment. But that's one idea, and we're looking for that in our data now. And I'll show you how we do that. But this is the ideas here. And then HETDEX comes along, and the photon travels, 12, 13 billion years. It bounces around in our optics at the end. And this is the last thing the photon sees after 12 billion years. This is the focal plane of the Hobby-Eberly telescope. This is about 20 arc minutes of sky, so it's like this big between my hands is the focal plane of the telescope. And you see those little tiny boxes are what we call an IFU, an integral field unit. Each box contains 448 fibers. We have 78 of those little boxes, and that makes the 35,000 optical fibers. We do a really simple experiment where we just point at one area of the sky, and we wait for a galaxy, and we hope to find a galaxy in one of these. In each exposure, in each little box, we get about 2 or 3 objects that we care about, and then we get hundreds that we don't care about. And so this is our data. And we do this, and we make like 400,000 of these across the sky, tile the sky, and make a map. And let me show you what that looks like. Okay, first, let me go back here. So that galaxy light comes in, and it gets dispersed, and it goes through a spectrograph, and this is what it looks like on our actual data. This is by far, I showed you that black hole image. This is by far my second favorite image that I've ever seen. And you look at it, you say there's nothing there. What is going on is each one of those 35,000 fibers gets put out into a spectra. So we're taking the light, dividing it up by wavelengths. We have blue light on the left and red light on the right. And we're looking for those dots. You can see those dots right there. There's one, there's a bright one down here. This galaxy is about 11 billion years old. This one's about 11 and a half, and this one's about 12 and a half. How did I know that? I knew that because they're more towards the red. It's the same light, but it gets redshifted. So you can look at this by eye, and you can find these objects. That's the whole essence of HETDEX, is generating these images. That's what comes off the telescope. And then we run a code that finds these peaks. That code, when we just so you know, when we first did, it's a very expensive code to run because we have a lot of data. This is why we have to use the Texas Advanced Computing Center. When I first did this 10 years ago, I hired a phenomenal coder. He wrote the whole thing in C and C++. It was great. He left, and the code was not so easy to repair. So then we moved it over to Python, because everyone's using Python. And Python just brought the system down, because Python sucks. But it's Python takes too long on the system. I am an old school coder, so I rewrote the whole thing in Fortran. Thank you. You know Fortran now. The problem is, though, it's a single point failure, and I'm the only one who can read the code. So I got to get this thing done. People are trying to redo it, but once I did the whole thing once I handled the whole thing from beginning to end, then it went so smoothly at that point. Then we actually were generating. So here's an example here of a fantastic source. You can see the top right has the peak of the emission. The dots are in the middle where all the light is. And we just need to know where in wavelength that is. And we get this beautiful spectrum in the middle there is the full spectrum. And you can see that bright line that's highlighted in yellow. That's an easy one. We have many of these. Here's a bunch. There's a bunch more. We have 5 million of these that we searched through. Okay? And then we got to turn it into our objects. Now the problem is, was very frustrating, is getting the code to try to understand the difference between what's a real source and what's a false positive or what's a defect in the instrument. That's where we're having a hard time. There's one object here that is a defect and everything else is real. The object that's a defect, is the one right where my finger is, right there, that one. That one's a defect. You can tell by the sharpness there. The human eye is remarkable at picking up these features. Okay, writing a code to do that is incredibly tricky. We do the best we can. We use AI, but there's nothing like the human eye. So what we did is we came up with a way, okay, I want to look at our data with all of our people, all of our team, but we have too much data. So I said, okay, I got to get a way to get it out to the public. At the time, my daughter was in high school, and she's constantly on her phone. I said, okay, got to get this into a phone. And so what we did is I had a grad student her thesis was to design this, and the actual data pops up on your phone, and if you like it, you swipe right. If you don't like it, you swipe left. So we call this Astro Tinder, and it worked. It kind of blew me away how well it worked. Right now, these are probably out of date. We have 4 million classifications, 20,000 volunteers. We've hit 85 countries. This is probably from a few months ago. I just haven't updated this one plot. You can go do this. We don't actually call it Astro Tinder. My dean gets really mad at me when I do that. We call it the Dark Energy Explorers. It's still active. You can look at our data right now. Right now, we, the public, the citizen science public, have gone through about 10-15% of our data. And then what we do, for one source, we make sure we have at least 10 individuals who have classified it. I was concerned that, a parent would give their phone to their baby and the baby would just swipe randomly. So we wanted to have some control over that. So we just averaged the 10 to 20 individuals, and it turns out that the accuracy is remarkable. That is, the average of 10 people is about 96% accurate compared to how I would classify something. So then what we do is we take that classification, and now we can pipe that into an AI, a machine learning algorithm, and then we train the machine learning, and then we apply that machine learning to the whole data set. But the basis, the truth, is the AstroTinder classifications. And it has really changed the system. I was kind of doing it as exploratory, as fun, to get more engagement from the public, but it is really useful. It's been great. So please help. And I always have I do these big classes of 270 students, and I do homework assignments. They normally hate homework. They love playing Tinder. And so I have them, they all do this like really fast and do a good job of it. Okay, so now I want to come back to engaging people, and I'll come back to HETDEX results here as well. Since I've been here, I've been wanting to get people out to the telescope. You of all people know the impact of being here where it's dark and appreciating the skies. Going to a telescope and looking through the telescope is maybe it's real because you own the photons. They get into your eye. You own them at that point. So maybe there is a connection that you get when that you get if you're not looking at a screen. So I've been bringing students out to the telescope. I've been running a project where my goal is to get every undergraduate out to the telescope every undergraduate who's an astronomy major. We have 180 of them now. I've gotten 35 out already, and I have 25 coming out this summer. And it is so much fun. I have them do everything. They run the telescope, design the observations, take the data, analyze the data. All I do is I drive them and I feed them. And that is pretty much it. They learn and then they teach each other. Here is them. This is from about 6 months ago in the 2.1 library room on top. And I love to compare it to the image of 1939. It's a little different. In the 1939 image, there's one person smiling, and it's the only woman in the whole thing right there. And up top, it's like when I bring the students out there, it's like a giggle fest. They are just having so much fun taking data. And then they're committed to analyzing it because they feel like they have some ownership of it. It is so much fun. We take them around to the HET, show them mirrors, and they just have a great time. They tell each other, they tell the other undergrads, and they come out. Here is an action shot. I was up there at 10 p.m. Trying to figure out. They're looking at, you can see that here. That's how this works. On the screen, right here, this is the globular cluster M3. I put that up there because we've just measured a black hole in that one. Ananya, right here, is the one who's doing the measurement, and it is so much fun to do this. So here's them. They solved the problem at 10 p.m. I go to bed, and I come up at like 4 or 5 just to make sure they haven't broken anything, just to make sure it's okay. And here they are. I got them at 4 or 5 a.m. They were totally asleep. The data, it makes a beep so they know to wake up when the observation's done, and then they take another observation. But that was a lot of fun. But this has been a blast. It's been working extremely well. Okay, and so that's related to the citizen science work. So this is the HETDEX. This is all HETDEX data on one plot. Every bit of data that we've ever taken. And go back to my laser pointer. So this is what's called a wedge diagram. We're in the middle. That's where we are. And then imagine you're looking out this way and this way. And the distance, this is the distance away from us. Okay, and so you see a wedge. The way we take our data is we have a bunch of data that's about 10 to 12 billion years ago. And we have a bunch here that's about 2 to 5 billion years ago. We don't have much in the middle here. These are, we did 4 fields: spring field, fall field, a special field, and then another special field. So this is all data on one plot. And then what we're looking for here is called a correlation function. So let's make up a correlation function for this room, for people in this room, and I'll explain how this works. It works very well. You are sitting in chairs. There are some who are standing on the sides, but you're primarily sitting in chairs. If I could measure each of your location, okay, and then for you who have my handwriting on your shirt, I measured the distance from you to every other person. You know, I do that. I go to all the people and I have all the numbers, what's called pair counting, for his position to everyone else. I do that to everybody else. For every person, I do these pair counts. And what you'll see is you'll see peaks. You'll see a peak on a scale that's about this much, maybe 3 feet. That's the separation between the chairs here. You'll see another peak that's maybe 4 feet. That's the separation between the rows. And you'll see a peak that's probably, 20 feet. That's this one side to this one side. And so if I had done that for humans in this class, in this room, I would be able to tell you how the chairs are placed. You say, Karl, we know how the chairs are placed. We can see them. But we can't see that in the universe. So you are the representatives of space-time. And so by your position, I can measure what the space-time is like in this room. I can tell you how they laid out these chairs, how they laid out these rows. And that's what we're doing in the universe. So here, I go to every galaxy. I do this pair counting, and this is what it looks like. There's, 10 to the 7 pairs, and this is the distance on the bottom there. And then I compare that to what a random distribution would look like, and I divide, and I get this. And what you're looking at right here, this is a random distribution in blue, and there's a bump right here. That is the bump that we're trying to get to. This is what we just play around with all the time. If I subtract these two, I end up with this signal here. That is the chair separation for how much the universe expanded over time. And that's this number right here. This is the distance to this specific scale for how the galaxies are distributed 10, 12 billion years ago, right there. I want to make a point that really, every time I look at it, and seriously, every time I look at it, I get claustrophobic. This is that same cone diagram that I talked about. We're now down here in the middle. There's our nearby group. There's our distant group. This red line, that's the observable universe. We cannot see beyond the observable universe. HETDEX right now is getting to about half halfway to the observable universe. You only model the universe once. You only make the map once. And that's what we're doing right now. We're not there yet, we're halfway there, but I got into astronomy because I love the insignificance. I love the vastness of the universe. And when I made this plot, the universe got small. It really got small because we're beginning to map everything in the universe. That's where we are. Okay, so now let me tell you the number. So the bump's at 148 megaparsecs at a redshift at an expansion time of about 11, 12 billion years ago. This turns out to a number of 223 kilometers per second per megaparsec. Bear with me here. So it's 220, so our number, that peak position, is 223 kilometers per second per megaparsec. Megaparsec is what we use for a distance in astronomy. The Andromeda Galaxy is about 0.8 megaparsecs away from us, just to give you a scale. And we always use kilometers per second. Well, we don't have to. We're in Texas, okay? We're in the US. We can switch to miles, a more natural unit, right? So let's switch 1 kilometer is 0.62 miles, okay? And then instead of I always hated megaparsecs. I prefer a mega light years, the distance light travels in a million years. So 1 megaparsec is about 3.26 mega light years. So you take 223 kilometers per second per megaparsec, multiply by the 0.62 to convert to miles, divide by 3.2 to get to million light years. Can anybody do that calculation in their head? And the answer is 42. 42 miles per second per million light years. So, and I am not kidding around. I had to obviously mess with the units, but that's what we came out with. I think that certainly deserves a free telescope, right? I want to get a free telescope. Okay, that's where we are. I want to leave you with just this image. Hilma af Klint is my favorite artist. I'm a big fan of Hilma af Klint. She has a magical way of trying to understand, comprehend the universe. On the right is a cartoon of the multiverse. She did that in 1915, and I think hers is a better representation. So I'm going to end there. Thank you. I'll take some questions. Oh, see, he's asking if the equation is a dimensionless. No. So what this is in, yes. I took out, so it is the expansion rate, so it's in kilometers per second per megaparsecs, but then I divide by the nearby value. So this is dimensionless, yes. Yes. Correct. So he's asking about the powers here. The photons are going as the fourth power. We understand that. This is basically time. So the contribution of photons goes as a power to the fourth. Contribution of matter goes as power to the third. And contribution to the shape goes as a square. And there's no linear term. So that's why I don't put any term in. You see, it's a function of z. So I am being agnostic as to about what that is when I draw that equation. Very good pickup. Yes. Good. He asked about that number 42. How does it compare to the other experiments that are out there? The major one is DESI. That's the Dark Energy Spectroscopic Instrument. This is the 0.5 billion experiment from the DOE. This is where I sat next to the head. And why? So, good question. Those numbers, their measure is at nearby universe. We pushed our result out to the distant universe. They are seeing a difference from what we would nominally expect for the cosmological constant. we are seeing right now the same for what you would expect for the cosmological constant. So there is a difference between what we get and what they get. We're at different times in the universe. Well, no, that's part of it. What I wanted to make, the point I want to make though, I'm going the wrong way, sorry, is we are looking at two different regions of the universe. So I can measure it this way and measure it this way. They're in here, so this is where Desi is, we're way out here, exactly. Right. Yep.
Okay, I've thought about this long enough that I wrote this question down. So I'm just trying to understand if this is in any way relevant to that wonderful equation you've got up there. So, what is the point of equilibrium of the acceleration that is occurring between when the gravitational force between two objects equalizes with the effect of the space-time acceleration? That point which you're no longer being pulled by the gravity and the space-time acceleration takes over. Is that what that equation is showing us? And how do you express that if it's not it?
I'm thinking as I take my time to go back to the equation. So you're asking, can you ask that again?
When you explain to us about how when you're close to something or farther away from something,
Yeah.
there is a certain gravitational force pulling you toward it. And as you get farther away, the space-time begins to take over, and there's a point where the space-time becomes greater and the acceleration faster than what you're already moving begins. How do you compute that?
Good. So what I'm not showing you in here, this Z is representative of time. So as the universe expands, okay, gravity's going to have a different influence, and space-time's going to have a different influence. So if you measure it, if you do the observations at different times, at different distances, then you can understand which one is changing, which one is the dominant one. Is it gravity or is it dark energy? That's why, excellent point, I don't want to go all the way back here, right here. That's why in this cartoon, right now, this experiment that we just talked about with Desi from the DOE has only measured it right about here. We're measuring it down here. It is that big baseline that's going to turn us into, okay, what is the theoretical models? The fact that we get a different result means either one of us is wrong or there's some weirdness in the universe that we don't quite understand. So that's how you break what you're asking is you do it at different times because they both evolve differently. Does that help?
Thank you.
Oh, my question is, wasn't your expansion rate of 226 kilometers per second per megaparsec about 4 or 5 times the Hubble constant?
Yeah.
Yes, it's bigger than the Hubble constant because it's in the past. We know the universe is slowing down. It's still expanding, and so it's like, in the early universe, you're going 100 miles an hour. Now you're going 50 miles an hour. It's going to slow down over time, and then now it's beginning to accelerate. So yes, in the past, that expansion rate was about 4 times higher than what it is now. Exactly right. Is that what you're asking? Yeah. Yes.
If you look at the shape and you take it literally, which maybe it's not designed, if you take it literally, it expands through the inflation. It seems to go into what I would maybe call a steady state to some degree, and then it seems to have taken off. Is that steady state just a slight expansion that we just don't see in the cartoon? It's always been expanding, and then it just took off logarithmically, or was there a steady state?
Okay. So it's always expanding. The universe is always expanding. It hasn't turned around yet. You can kind of see a slight turn around here, but instead of going 80 miles an hour, you're going 75 miles an hour. You're still expanding. You're not going a negative velocity. You're not coming together yet. So it's just it's the shape, it's how that expansion changes over time. This is where dark energy takes over. It curves out.
Got a question back here?
So modified gravity seems very easy to understand, right? You just modify gravity. Is there any kind of model that fits the data pretty well, or is there a disconnect between the two?
Right. So yeah, I think 1,000 physicists just cringed when you said it's really easy just to modify gravity. People have been working on this for a long time, and the problem is there's a lot of constraints you need to pull in. The sun going around the Milky Way, well, you need to model how the galaxies interact. So modifying gravity, while it seems really, for me, it's really attractive, right? We've done it before, a big deal, let's change it again, we've done it before. But we haven't had that explained, for example, where galaxies come from in the early universe. And if you tweak it in one spot, it's beginning to have an effect on the spot. So there hasn't been a nuclear model yet. Well, that doesn't mean it's not. That doesn't mean it's not correct.
We have time for one more question.
Okay.
Yeah, one more, here we go.
So you're measuring the expansion rate of the universe by looking at baryonic acoustic oscillations. You have another team, Adam Rees, who measures the expansion rate of the universe by looking at supernova, type 1a supernova and other galaxies. You get a different answer. You get one answer for the expansion rate. You get another answer when you do it with baryonic acoustic oscillations. You got a crisis in cosmology. Where are we right now in terms of resolving that crisis?
You'll get a different answer that we can talk to. I would say it's been shown that the supernova is biased. The supernova folks would say that there is new physics in the universe. That one way to explain why there's an excellent question. One way to explain why there is a difference in measuring expansion rate locally, supernova, compared to measuring in the distant universe, baryonic acoustic oscillations, is because there's physics that changes in the universe. There's something going on that we don't quite understand. I do not subscribe to that. I do not think that's right. I think it's something in the data. And once I'm done with that, I'm going to jump on some of the other data. Now, with the supernova, I think there is one argument is that we live in a potentially volatile bubble. It's really hard to, again, if we're in a bubble, all these models assume that everything is smooth. If you have like a slight underdensity, the expansion rate will not be quite what you think. That's one potential out of this.
Okay, we had a last minute question. Here we go.
If both space and time are expanding simultaneously, what is it expanding into?
Okay. Yeah, how about that? Okay, let me try this. So that's an excellent question. It's the one everyone thinks of. Let me do the analogy to the Earth, okay? And say we are creatures, and we are creatures on the surface of the Earth. Say the Earth began to expand. Let me back up a bit, and then I'll come back to the expansion. There's the surface of the Earth. Now let me ask you the question. Tell me, where is the center to the surface of the Earth? It's Texas. No, I mean, there is no center to the surface of the Earth. Analogous, there's no center to the galaxy, to the universe. Let's now talk about the expansion. If the Earth were to expand, okay, just imagine it expanding like a balloon, then we would just be sitting here saying to each other, when is this guy going to stop talking? And as the universe is expanding, you're going away from me. As the Earth is expanding, you're just sitting there happily, but your fellow TSP members are moving away from you. And the roof is falling, but we don't ignore the roof. But that means you're measuring this expansion. We're not expanding into anything. It's just the structure of space-time is expanding. Now, one way around that is for our universe is only defined where there is space-time. our individual universe. If I went back to the concept of the multiverse, then you can have space-time outside of that. And then you can talk about expanding into the multiverse. But did anyone pick this up? And I'll tell you exactly what we're expanding into. Hold on, and then we'll be done. Where is it? So, this is the edge of the observable universe. This is my idea of what's beyond the observable universe. So, expanded into Prince. But no, so we don't know, and so that it's possibly we don't understand the math within. That's why I keep talking about space-time. Once we get space-time, then we should be able to answer these questions. I just don't know at this point. So the best way to end this is to say, I just don't know. Thank you.